Hello everyone, my name is Ramtin Afshar, and today I want to talk about parallel network mapping algorithms, which is a joint work with Matias, Goodrich, Pedro, Matias, and Osegueda. So in graph reconstruction, motivated by network mapping applications, we are given a set of nodes of a graph G, and we would like to discover the HZE. So we can access the following black box oracle in this paper, which is called distance oracle, and given two vertices u and v, it's going to return the number of edges on the shortest path from u to v. So for example, in the below graph, you can see that given vertices b and g, the distance of b and g is just 2, and by the highlighted path. Okay, so motivated by distributed nature of network mapping applications, we are interested in designing parallel algorithms. So we evaluate our algorithms using the following performance measures. The first one is query complexity, which is the total number of queries that we issue to our oracle. And the second one is round complexity, which is the number of parallel rounds that we issue our queries. So the queries that we issue in each batch may not depend on the answer of the queries in the same batch, but it may depend on the answer of the queries in the previous batch. So we first improve the graph clustering technique of Theorem, where we allow the number of centers, where we allow the number of rounds to be any value between O of 1 and O of log of n, whereas the Theorem algorithm just implied an O of an expected O of log of n rounds. And this is the application, for example, in balancing graph theoretic Bernoulli diagrams, where it allows the number of centers to be smaller than it used to be. And then we compare our algorithms with the previous best one. So when it comes to the algorithms with just constant number of rounds for graph reconstruction, there is just a trivial work, there is just the trivial algorithm using O of n to the square number of queries with constant number of rounds. We present the first subquadratic algorithm with O of n to the third half plus epsilon. And for the non-parallel algorithms, there is a previous work by Cannon et al. Using this amount of queries, where we present a parallel version that it takes O of log of n, but it also improves the total query complexity. And our bonds hold with high probability, whereas the others of these two papers prove their bond only in expectation. So let me illustrate the sketch of our network mapping algorithm. So we first choose a hand-picked set of vertices which are well distributed as our set of centers, and then we use this set of centers to compute a graph theoretic Bernoulli diagram. And now the thing is, if we decide to do the brute force in each of these cells, we manage to discover all of these internal edges that they are in the same cell, but we cannot find the boundary edges. And now, if we would like to find the boundary edges, we argue that if we extend each of these cells slightly, so for example, the cell that's centered at A4, if we slightly extend it, would look like this, and the cell that is centered at A1 is going to look like this if we extend it. And now, if you perform brute force for each of these extended cells, it's going to discover all of the edges. And we'll see later why. So let me present our graph clustering technique first. So given a weighted unweighted graph G with the distance metric delta, so note that in graph clustering technique, we may assume that the graph may be weighted, but in our network mapping algorithm, the graph may not be weighted. So given a set of centers A as represented using just green color, we define a cluster with respect to vertex, the cluster of W with respect to this set of centers as the set of nodes that they are closer to W than to any of these nodes. So just look at this as, geometrically using the Euclidean distance for the purpose of illustration, we can see that the cluster of W would be just these two centers. And now the idea here is that we would like to find the centers A such that both the set of centers and also the cluster sizes are all small. And a very simple observation here is that as we add more nodes to the center set, it's not gonna let the clusters to be swell, and it's gonna just let it shrink or remain the same. So if you add this node to the cluster center, it's gonna just bring this node out of the cluster of W, while if we add this node, it's not gonna affect the cluster of W with respect to the center A. So we call a center A beta and S-Balance center if all of the clusters have the size at most beta times n over s. So we essentially would like to provide such set of centers. So let me present our parallel center algorithm. It initializes a set of centers to be empty, represented using green color, and the set of W, which is the set of nodes that they have huge clusters, meaning that their cluster size is greater than beta times n over s. So we essentially would like to provide such centers such that the cluster of each of these vertices is small enough, meaning that their clusters is at most beta times n over s. And beta is a parallelism parameter that we introduce in this algorithm. And S is a sampling probability parameter. Sorry. Okay, so what W is not empty, we add a sample with expected size of S to the set of centers from W, and then using these two nodes, we recompute the cluster for each of the cluster for each of these vertices. And after finding the cluster size for each of these vertices, which is just illustrated for just 4 vertices A, B, C, and D for the for illustration, but it has to be for all of the vertices. We remove the nodes from W such that they have a small enough clusters, and then we perform another iteration by picking another sample from W and add it to the center, and then again we recompute the cluster sizes. And we continue doing this until all of the cluster sizes are at most beta times n over s. And then we just return the set of centers as a beta and S-Balance. So the key idea here is that when we remove a node from the set of W, it's gonna be fixed, because when we add more nodes to the centers, it may not let the cluster sizes to be increased. So all we need to prove here is that how many iteration it takes to find this set of centers, and what is the sizes of these centers. So the following theorem establishes the fact that our algorithm takes O of log of n in the basis of beta parallel runs to give us a O of S times log of n in the basis of beta parallel runs. And this just means that if we set, for example, beta to be some constant, it's going to just take O of log of n runs. Whereas if we set beta to be n to the epsilon, it's going to just take O of 1 runs to find such centers. And it definitely, as I said, returns the beta and S-Balance centers. And in order to see how many iterations it takes and what is this center size, we need to note that the sample function returns a sample size of at most 2 times s with probability 1 minus e to the minus s over third, and then it just holds with high probability across all the iterations when s is at most 6 times ln of n. So all we need to prove here is that the number of parallel runs is O of log of n in the basis of beta. So for this, I would like to invite you to take a look at our paper for more details. So let me provide a sketch, a better sketch of the remaining work to be done. So we first find the beta and spalon centers. We then use it to compute a Voronoi graph theoretic Voronoi diagram. We extend each of these cells, and then we perform our brute force. But a challenge here would be to compute the cluster sizes at each iteration in the parallel center algorithm that we designed. And in order to handle this, we instead use a sampling to estimate the sizes of the clusters. So we take a global random set R from the set of vertices to estimate the cluster size for each of these vertices, and we just scale it up to the according to the sizes of this sample. And for more details, please just refer to our paper. Just for just to wrap this up, I would like to provide some intuition about how we cover all of the edges. So given a set of centers A, let's say that there is an edge like U and V in E, then we can prove that there exists a center A, such like here, such that both U and V, they are either in the neighborhood distances of A, meaning that they are in this small, or there exists a node with distance at most 2 of this center, like for example W1 or W2, such that their cluster wholly includes the the vertices U and V. And this just means that having a set of centers A, in order to cover all of the edges, all we need to do is to perform a brute force for each of the neighborhood distances of A, and also for each of the clusters that they are in this ball. So yeah, that would be all. Thank you very much for your attention.